We are live, and this is Problem Solving with Systems of Equations. And this is part 3. And for this one, we've got a word problem that's actually very, very small, which is nice. Less scary, right? The problem is it's going to have a lot of information packed into very few words. So in this case, we're going to be paying extra attention to vocabulary and possibly formulas because there isn't much here. So, word problem, helpful hints. Number 1, read through the problem. Is it a type you recognize? Are there formulas? So let's take a look. The difference, okay, already vocabulary, right? That's subtraction. Of the measures of two complementary angles is 30 degrees. Okay, so now we know this is geometry. Find the measure of each angle. There isn't a lot there. However, we can start off with some formulas. So what are the formulas? Well, when two angles are complementary angles, pardon me guys, I'm going to move everything out of the way just so I can write it down. Complementary angles are angles which, when you add their measures, like here if I have A degrees, and here if I have B degrees, you can kind of see from the image, the drawing that I wrote, A plus B equals 90. So complementary angles are angles whose measures add to 90. And you might be remembering also that there's another word very similar called supplementary. If they're supplementary, then they go together to make a full straight angle. So they add together like this. So this angle and that angle go together to be 180. So complementary is 90 degrees. And fun fact, we aren't actually told anything about the situation, but I drew them as if they were right next to each other, which is called adjacent. They don't actually have to be adjacent. Complementary just means that when you add up their measures, you get 90. They could be anywhere. So there could be one of the angles is over here and one of the angles is way over here. They don't actually have to be on speaking terms. So we've got complementary angles. You look so nice. Oh, so do you. Oh, so do you. I love that shade of green on you. Oh, and that blue makes you look like such a great carnivore. Oh, thank you so much. Okay, so complementary angles, they add to be 90. So this says the difference of the measures of two complementary angles is 30 degrees. So there's a lot packed into this. I'm going to say, let the measure, I'm going to be all formal this time. Let the measure of the first angle be A. And then I love using ditto marks. Now, I may have these ditto marks are not exactly, if you've got things that turn corners and such, ditto marks are a little tricksy. But basically, these little marks say it's the same thing as above. So let the measure of the first angle be A degrees. Let the measure of the second angle be B degrees. Okay, so I'm using A and B. Could you use X and Y? Yes, absolutely. Could you use smiley face and flower? Yes. Could you use anything else you can think of? Absolutely. You get to choose the variables when the problem does not give you the variables. Okay, now this is an interesting situation because we have the complementary angles, but we also have, and this is like an onion, it has layers. We also have the difference of the measures of these angles is 30 degrees. So now we have a different statement. This is the blue one. The difference in the measures is 30 degrees. So this is complementary angles are the sum is 90. the difference means, and here I don't know which one comes first, so I'm going to just say A minus B equals, right, is equals 30, like that. The difference of the measures equals 30. So let's combine all of our information. I have this blue statement here, and I have this pink statement from the fact that they're complementary here. So altogether, I have A plus B equals 90, and I also have A minus B equals 30. So notice that there's quite a lot packed in. That's basically one sentence gives us both equations. So this is an unusual situation. Usually one sentence gives us one equation, but in this case, the pink part right here gives us the top, and then the whole sentence gives us the bottom. Now, what's great about this problem? Well, what's great about this problem is they're perfectly set up to use the elimination method. And I don't have to change them. A plus B equals 90. A minus B equals 30. I add them. The plus B and the minus B cancel out. So I get 2A equals 120. Or A equals 60. Oops, there you go. And then if I know that A equals 60, then I can use that information and I can say, wait a minute, I'm going to go backwards. It's a little weird, but I want to use this space. If A equals 60 and A plus B equals 90, 60 plus B equals 90, B equals 30. So altogether, A equals 60, B equals 30. The measures of the two angles. Now, again, I'm taking advantage of the fact that I declared my variables up here. So I'm just giving my answer in terms of the variables. But you can also give your answer as 60 degrees and 30 degrees. All right, you can actually write out the angles like that. So let's double check. Let's see if these actually work. Let's come up here. The difference is 30 degrees. So is there a difference between 60 and 30? Is that 30? Yeah. Okay. And are they complementary? When you add them together, 60 plus 30, you get 90. Woohoo. So even though this one started out, I think in some ways much more confusing, and you had to know the formula, once you've got the formula, the problem itself went very, very fast. Woohoo. Okay, so throwing caution to the wind, I would like to do the next problem. Now, at this point, I am very much hoping that you have been working on mixture problems. Anyone who's watching this, because there is a particular way that I solve mixture problems. If not, that's okay. I'm going to show you. And I'm also going to show you, because here's our little hint. I haven't even read through the problem and I'm already telling you it's a mixture problem. And that's because my brain already saw, let's see, I haven't used orange yet. Mix. The word mix. You would like to mix. I also see percentages. These are classic mixture indications. So this is a mixture problem. Once you recognize that, there's a very particular setup. So let's read it. You would like to mix a cleaning solution containing 13% ammonia. Okay. You have a 4% ammonia solution and a 16% ammonia solution. How much of each will you need to use to obtain 1 gallon, which is 128 fluid ounces, of a 13% ammonia solution? So why is this called a mixture problem? Well, literally, we're making a mixture. We're mixing two things. Now, once you recognize that it's a mixture, I have some suggestions. There are many, many ways to solve these problems. You do not have to do it the way I'm going to recommend, but this is the way that has been really consistently successful in classes. So let me show you. The first thing I'm going to do is I'm actually going to show you that it makes sense what we're actually asking to do. So I'm going to draw a little line. And on one end, I'm going to write 4%. It's like a number line, but it's for percentages. On the other end, I'm going to write 16%, right? We've got a 4% solution. 4%. And by the way, you might be saying, what the heck is a solution? Aren't we looking for a solution? And the answer is, in chemistry, a solution, especially in this case, we're assuming it's you ready for a cool word? Aqueous solution. We're assuming that this is a water mixture. So solution is when you mix something in water or in something that's liquid. So in other words, when I say 4% ammonia, that means only 4% of this big jug is actually ammonia. The rest of it is something else, water or something. And when we say 16% ammonia solution, we're saying 16% of this is ammonia, but the rest of it is something else, probably water, something that won't interact with the ammonia. And then I want 13%. And so my question is, where does 13% lie on this? And so if you add these two together, you get 20, and half of that is 10. So the halfway mark is 10%. If you added equal amounts of 4% and 16%, you'd end up with a 10% solution. And then it would be done. It would be really easy. But in this case, they don't want a 10%. They want a 13%, which is right there in the middle of those two. This is what we're going for. This is the magic mixture. So a couple things that you have to make sure of. When you're doing a mixture problem, the thing you want to get, the mixture you want to create, has to sit between the strengths of the other two. So in other words, it's not possible to mix a 4% and 16% and end up with something that's got 30% ammonia. It's just not possible. You also can't mix 4% and 16% and get something that's like 2%. That's too small. It's got to be between them. So it's 13 between them. Yes. Okay, next thing. The 13% being closer to 16% than it is to 4% tells me I need more of this. What if it's in the middle? What if we wanted exactly the middle percentage? Then we'd have equal amounts of them. Since this is closer to 16, we're going to use more of the 16%, less of the 4%. Okay. Do you have to do this? No, you don't. But a lot of people find it helps to kind of think about the problem ahead of time. Feel free to use it or not as you see fit. Once it's a mixture problem, I'm going to recommend a certain setup. And again, do you have to set this up? No, absolutely not. You do not need to set this up. But I'm going to set up a box, big as it'll fit. And I'm going to start off with a top row that's going to give me room to write out everything that we're going to be doing. And then a leftmost column, and that's also going to allow me to write in some titles. Now I need spaces below the top. The top is just for the titles. Then I need the first solution, the second solution, and then the mixture. So let me label this so you can see. The first solution goes right here. I'm just going to write 4% because that's the first one I see. And then there's a 16%. These are the two that we're going to mix. We're going to mix those. And then down here, I write mixture, or some people like to write blend, whatever you like. This is going to be the 13%. Now, I hear you already asking, what goes there? Well, smiley face, because of course, word problems. Now, at this point, if I were you and I'd never seen this, I'd be like, oh, this is great. How am I ever going to learn this? And the answer is, every time you have a mixture problem, the method I'm showing you will work. There's some slight changes we need to make, and spoilers, in the next video, the last problem we're going to do, also a mixture problem, it'll look a lot like this. So I'll show you how to adjust this chart to fit lots of different things, or at least one other thing. Okay, now this is the part that gets difficult. But here's the thing. This chart is for you. So as far as I'm concerned, you can write whatever you want in it. This is to help you organize your thoughts. But this is what I recommend. The first column is going to be the total amount. The second column is going to be the percentage, in this case, the percentage of ammonia. And the third column is going to be the column that will say amount of ammonia. Okay, so total amount, the percentage of ammonia, and the amount of ammonia. So now let's look back at the problem. All of this chart gets made without having to read much from the problem, but let's check. Do we have any quantities? That's going to go in this first column, the total amount. And I see that I have 1 gallon of the total, which it then says 128. I'm just going to say ounces. They are fluid ounces as opposed to a different type of measurement. And I see in the question, how much of each will you need to use to obtain this final blend? So I'm going to need variables. And I think a lot of people use X and Y, so I'm going to use X and Y here. Now, here's the thing. You may have learned to do this using X and 128 minus X. That's fine. You can do it that way. I'm going to show you this method with X and Y just to show you how it goes. But you, again, you get lots of flexibility how you approach these problems. The percentage ammonia is 4%, but I'm going to write 0.04. So I'm going to write it as a decimal. 16%, 0.16, and 13%, 0.13. The thing is, percentages really don't play well with others. So we switch things, we convert them into the decimal form so that we'll be able to use it in the rest of the problem. Okay, now here's the amazing thing. If I take, let's look at the bottom because I think this one's a little bit easier to understand because it's more concrete, pardon me. Ooh. If I take the 128 ounces and I multiply times 13%, so I take 128 times 13% in the form of a decimal, and these ones that we call mixture problems or science problems, you're going to need your calculator for most of them. So if I take 128, but only if I get 128, there we go, times 0.13, I get 16.64. Now this is in ounces. And what does that mean? Well, that means that out of the 128 ounces, right, this thing is a big jug of cleaning solution. Only 16 ounces of that is pure ammonia. The rest of it is whatever we added. It doesn't tell us anything about the solution, so I don't know what we added to the ammonia, but whatever it is, it's the rest of it. So what is that? That's like 112, 111 ounces of just something else. And so this is the cool trick we can do. We're going to keep track of the total amount, but we're also going to keep track of the amount of ammonia. Now, I hear your wheels thinking in your head. You're like, wait a minute. If there are two variables, we need two equations. And I'm saying, ding, 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 ding. There's going to be an equation here, and there's going to be an equation here. So we're being very clever about setting this up. So the equation basically writes itself. If you have never used a chart for a mixture problem, I can almost guarantee that you're looking at the screen thinking, what is even happening? And so what I would encourage you to do is practice. Because once you get used to this chart, most people, not everyone, some people may hate it, that's fine. But most of the students I've ever shown this to, they're like, whoa, I can write down all the information here and then I don't have to worry about it. And the answer is yes. That's the goal, that this will be an organizing chart. So, and again, if you don't need to use it, if you just want to come up with the equations, that's fine. Once you see the equations, you might think, oh, I could do that without the chart, in which case, don't worry about the chart. Okay, obviously in this video, I'm getting paid for every time I say the word chart, 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 chart. Okay, so what we're going to do is as we move across the chart, because of the way it's set up, we're going to multiply. Okay, so I'm going to take the total amount of the 4%, that's x, times 0.04. And I'm going to write the 0.04 first, because that's convention. So we multiply these two things, multiply. Next line down, we're going to take those and multiply. Notice that because we don't know these amounts, we have to leave these as just algebraic expressions. That's okay. We'll get to the point where we're going to be able to use them. Are you guys ready? I'm very excited. I don't know if you guys are excited. I'm pretty excited. Okay, I'm going to take you a little bit to Smeary Town, but it's for a good cause. That first column where it says total amount, we get x plus y. So the amount in the first one plus the amount in the second one has to be the total amount. There's nothing, we're not adding anything else. So x plus y has to equal 128. That's our yellow, or our first equation. Woohoo. Okay, second equation, we cannot add these. If you look, 0.04 plus 0.16, that's not 0.13. That's not the way percentages work. Percentages can be tricksy little creatures, so we're going to just leave that alone. And I'm going to go to this last column, as I said, and we're going to keep track of how much ammonia there is. Now, this equation is going to be more complicated. Take a deep breath. Get some hydration, right? Make sure your friends are close by. Hello, Sharktopus. Hello, Godzilla. Okay, and then I'm going to use this one here. 0.04x, so 4% of x, plus 0.16y equals, and remember we're multiplying, so here I don't get 128, I get just the ammonia, 16.64. And that's the blue equation. And now we are home free. By which I mean, now we've set up the problem so we can actually solve it. So mixture problems, these are not things you want to do when you have to run out in 5 minutes. These are the kind of problems that you need to really set aside some time. Generally speaking, you can get pretty fast. Like if I really push myself, I could solve this in like, I don't know, 5-10 minutes. But that's if I really pushed hard. I think most people just taking their time and writing it down, this is a good 20 or 30 minute problem at least for most people. So give yourself some time, but we have two variables appearing in two simultaneous equations. Yay! Okay, now these are complicated enough that I'm not even going to try to start. I'm going to go ahead and I'm going to say, you know what? We're going to write this all on another page because this is too much. So I've got x plus y equals 128 and 0.04x plus 0.16y equals 16.64. And I'm going to use elimination. Now I'm going to stop here for a second and remind you we're adding 4% to 16% to get 13%. We want to get a total of 128 fluid ounces. So looking at this information, you can kind of see how x plus y is 128 and 0.04 times x plus 0.16y equals 16.64. So this is how some people get so good that they're just like, read this problem, come up with these equations. And if you can do that, that's awesome. So first thing I'm going to do is I'm going to multiply down in the second equation by 100. Okay, 100. Why 100? Well, I want to get rid of the decimals. Do I have to? No, no. you can work with the decimals, but I find the decimals to be kind of, it just confuses my brain a little bit. So I'm going to clear the decimals by multiplying by 100. So 100 times this, move the decimal point 2 places, and I get 4x plus, move the decimal point 2 places, 16y equals, remember, multiply everybody by 100, right? Everybody gets a 100. This is the distributive property. 100 times this, 16.64 becomes 1664. So it's kind of nice. All the decimals went away. Now, in this moment, what I'm going to multiply on top? Well, if I want to be thoughtful about this, I want to cancel this 4x, or I want to cancel the 16y. I've got x and y, so either I'm going to multiply by -4, or I'm going to multiply by -16. I'm going to go with -4 because it's smaller. -4x minus 4y equals, and then I need a calculator for this. I have to multiply -4 times the 128, which I know some of you could do. And I think it's 512. Is that, did I get it? 128 times -4 equals -512. Brilliant. This is why they pay me the little bucks. Okay, let's hydrate. Remember to hydrate. Okay. So what did we do? I cleared the decimals, and then because I wanted to save space, I multiplied up top by -4. And notice those two are going to cancel out. And so I'm going to get -4y plus 16y is 12y equals, and again, I'm going to check with my calculator, although I could do it probably in my head. 1664 minus 512 is going to be what? 1152. Is that correct? 1664 minus 512 is 1152. Okay. Divide both sides by 12. Do you guys feel lucky? Shall we try? I don't know if it's going to work out exactly. Oh my goodness, what an amazing thing. Y is 96. It's even. Will it always be even? No. When you're dealing with decimals like this, there are going to be some nasty answers, but this one was pretty nice. Okay. So at this point, hopefully you're feeling very used to this part where I say, are we done? And you're going to say, no, we're not done. We need to find x. We know what y is. Now we need to find x. Well, the really cool thing about mixture problems is usually one of the equations originally is a very simple equation. X plus y equals 128. And I know y is 96. And let's see, what did I end up with? Oh, I'm going to guess it's 32. Shall we check? 128 minus 96 is 32. Woohoo! X is 32. And again, in my class, if you set up a beautiful chart like this, you've declared variables. So you could go ahead and just tell me that x equals 32 and y equals 96. Now, in some settings, you may want to be more formal. And if you want to be more formal, then we can go back. The nice thing about this chart is it keeps all the information. If I say, okay, x was, which one was x? I can look and see, oh, that's the 4% one. So I could write 4% ammonia. I want 32 ounces. Remember that the shorthand for ounce is OZ because, you know, non-metric system. And then the other one was the Y was the 16%. So 16% ammonia was 96 ounces. Ooh. Now I hear you all saying, but how do we check it? Well, the answer is you could plug these back into the equations and make sure they work. For example, 96 plus 32 does equal 128. And you could plug it in here and make sure the whole thing works. But what I like to do is I like to double check right here. Remember when we set this up, I said, okay, 13% is way closer to 16. So we need more 16, a lot less 4. So let's look here. 4%, 32, 16%, way more, 3 times as much. So at least for what we estimated, it makes sense. How do you know when you get one of these wrong? Well, these are really hard because a lot of people can't estimate these numbers. So just looking at it isn't going to give you the answer. But you'll know that something went tragically wrong if you get a negative number. All the numbers should be positive. If you get a negative, then something is weird. If one of the numbers, like how, remember we had a total of 128 ounces, if it asks you to have 400 ounces of one of them, that would be really weird too. So if any of the numbers are negative or too big or just weird, I would recommend redoing the problem to the best of your ability. You guys are awesome. We did 2 more problems. You're amazing. You're so smart. Don't let anyone ever tell you differently. And remember, complementary angles, 90 degrees. So you look very nice. So do you. Ooh, 90 degrees. And mixture problems. Remember this. The very next video I'm going to make is another mixture problem, slightly different. And so we'll get to practice with this again. Woohoo. Rock on. Math on. Woohoo. You guys are awesome.